Interpreting skews. We've learned about skews, whether it is positively skewed or negatively skewed, and if there isn't a skew, then it's symmetric. Here's an example of box and whisker representing symmetric data sets that are plotted on a column graph. So as you can see, this column graph is describing discrete data, right? Because there are gaps in between our columns. Symmetric, when we look at the box and whiskers, you can see that the box, which represents our interquartile range, right? This is symmetric. On the left and on the right, two boxes of the median, which is our Q2. We have two whiskers sticking out, which are also symmetric, the maximum and the minimum. So when everything is symmetric to the median on the right-hand side and on the left-hand side, whether it be the boxes as well as the whiskers, we can say that this graph is symmetric. Let's take a look at positively skewed. So the box and whiskers tells us that this is positively skewed by the length of the whisker to the right, which tends towards the positive end of our axis typically, right? And we also see that our upper quartile range and the median, that rectangle, is bigger, larger than the lower quartile range, Q1, with our median Q2. And our whisker to the left is a lot shorter. So this tells us that most of the data generally is skewed to the right, so we have more data towards the positively side, hence this is a positively skewed data set. Negatively skewed, you can see, would be the opposite, right? So your lower quartile and your median, that box is going to be larger than your upper quartile and your median box. So Q1 and Q2 box is going to be larger than your Q3 and Q2 box. Same goes with the whiskers. So the whiskers towards the negatively skewed, it tells us that a lot of data, not most of the data, but quite a bit of data ranges from your Q1 all the way to the minimum. And there's very little data range between your Q3 and your maximum data. So this tells us that the data set tends towards the negative side. You could see that these three are three different types of graphs, right? So this tells us the numerical variable, so our data set, whether it be discrete or whether it be continuous, and we covered that last class. Now let's take a look at outliers. In order to represent outliers, we must have an upper boundary and a lower boundary. What that means is outliers, we know, is a general body of data, and the data doesn't fall within this general body, so it's either too big or too small. In order to determine what the boundary is for this general body of data, we need to figure out what the upper boundary is and what the lower boundary is. So if any data point falls outside of the upper or the lower boundary, then we can assume that that's an outlier. In order for us to find upper and lower boundaries, it works perfectly by utilizing our quartile ranges. So let's take a look at our example. We've been using this data set. This data set, what we could do is we could plug it in to the upper boundary and lower boundary equations. Upper boundary equals to your upper quartile, which is your Q3, plus your 1.5 multiplied by your IQR. In this case, our IQR is 5, our Q3 is 8. So we plug those data points, that information, to figure out the upper boundary. We would do the same thing for the lower boundary. Instead, we would use lower quartile, and instead of adding, we subtract because we want to find the lowest boundary. So in this case, this is the value that we would get. Upper boundary, 15.5, and lower bound at negative 4.5. So if we have any data points, say we have an 18, then it means that that's kind of an extreme value and it falls outside of our upper bound, which means that that's an outlier. If we have a value, say it's negative 5, that's still 0.5 more towards the left outside of our lower bound. So that means that that negative 5 would also be an outlier.